Let's go through the working with data in R activity. So what I've done is I've loaded up RStudio, and one thing you want to make sure is that you have the most current version of R, which is 3.3.2. Now, if you have an older version, what you need to do is head over to CRAN and download and install the most recent version, and that way when you load up RStudio, you'll see that you'll have the 3.3.2 here. Alright, so I've headed over to Blackboard and I've clicked the link for the RMD file for this activity, and I can go ahead and click it again here. And what I'm going to do is to open it up in RStudio. I'm actually going to go to Show and Finder and open up the one that I downloaded previously. And what we'll see is the title, author, etc. You're going to want to change the author to whoever you are here. And the first thing you're actually going to want to do is to make sure the package knitr has been installed. Knitr is what allows us to knit a document into an HTML file, a Word document, etc. So the first thing that I want you to do actually is head on over to the console window and type in the install packages command, and then in double quotes type in knitr, K-N-I-T-R. And what this will do is it'll download and install knitr for you along with a whole bunch of other packages that are required. And this way, once this is done, you'll be able to knit this button right up here into an HTML file or to a Word document that you can further edit. Alright, so another thing we can make sure that the installation was successful by typing in library and then knitr, and now we're ready to go. So the purpose of this activity is to start to become an expert at data manipulation. We know that 80% of any analytics project is going to be spent merging together data sources and manipulating data, cleaning data, and so we need to get our feet wet here. We're going to start out by working with one of the data sets that have been built into R, the mtcars data, and we can load that up into the environment just by running the line data and then in parentheses mtcars, which has been written out for you. Now there are a few ways to go about doing this. You'll notice the run command here has a little arrow, and you'll notice that run selected lines has a shortcut, and I'm going to stick with this shortcut as best as I can. On a Mac, it's that command and then return key. On a PC or Windows, it's slightly different. So I'm just going to have my cursor on this line and do command return so that it runs that line here. Notice it gets sent down here to the console window, it's run, and we see that the data file is now in the global environment tab. Alright, so what are we asked to do? We're asked to find the dimensions, basically the number of rows and the number of columns of the data frame, and look at the first 3 rows using the head command. So let's go ahead and find the dimensionality of the data. The command is dim, and we just say what the name of the data frame is, whose dimensionality we want. Command return on the Mac tells us that, all right, we have some numbers here, 32 and 11. The first number corresponds to the number of rows. The second number refers to the number of columns. And you'll notice actually now that we've done something with the data, it's keeping track of some information with it. So there's 32 observations, 32 rows with 11 variables. Clicking on this blue arrow here gives you a preview of what the column names are, what type they are, and then also some of the numbers in there. All right, what if we just want to look at the first 3 rows, print that to the screen? We can use the head command to do that. Head prints out the first few rows. Tail will print out the last few rows. If we want just 3, we can add an additional argument 3 here to get those first 3 lines. So I'm going to have my cursor on this line and then command return to run it. And one thing you'll notice compared to previous versions of RStudio is now actually it will start embedding some of that output into the RMD file itself. Now you may like this style, you may not like this style. There are some options to turn it off if you do not like it. But for now, we're going to keep it so that we can actually see what the result of running these commands are inside the RMD file. All right, so question 0 says, all right, let's start working with this data frame here. Actually, before we even do that, let's get a little practice with vectors here, one of the core ways that R stores data. So we want to create a vector with integers 1 through 10, 12 through 15, and 20 through 50. Now, there's a shortcut for this because if we want the integer sequence, like 3, 4, 5, 6, 7, and 8, all we need to do is have the smallest number and the largest number separated by a colon here. So 3 colon 8 would be the numbers 3, 4, 5, 6, 7, and 8. If we want to create a vector, well, we know a vector is created by doing the C command, like concatenate, C and then parentheses, and we put in parentheses what we want. Well, we want the integers 1 through 10. That'll create the sequence 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we also want 12 through 15, and we also want 20 through 50 here. When I run this line, we see that the output shows that this is the correct answer. It also shows it down here, and now we're good to go. All right, so let's start working with the data a little bit. Let's define a vector called x, whose values are those in the MPG column of the MTCARS data frame. All right, well, we define a quantity by using the left arrow symbol here. We're going to call it x, so the name of our variable goes on the left, and the left arrow symbol is simply the less than followed by the dash. And what do we want it to be? Well, we want it to be a particular column of MTCARS. We know that we can extract a particular column by typing out the name of the data frame followed by a $sign. And notice RStudio is being helpful to actually showing you what all of the columns are. We can either select this from the list or we can just type it out. I'm just going to click on this, making sure that there's no space in between the $sign and the rest of the words. So I'm going to run this command here. What you'll notice is that there is no output that's displayed in the RMD file, and that's because something is going on internally. If I look back at the global environment, I see that R is now aware of a quantity called x. It's numerical, and here are some of the numbers that are inside it. All right, so let's verify that x is indeed a numeric vector, and let's do some things with that vector here. So how can we tell what type of object the quantity x is? Well, the class command lets us know. We run class x, it says, okay, numeric. What are the options? Well, it might be numeric, might be character, might be integer, might be factor, a lot of other objects. Data frame is another object, and we're verifying here that basically that x is a numeric vector. All right, what about the 5-number summary, the minimum, the maximum, all those good things? Well, summary is our command to get the basic summary statistics. And we see that here's the 5-number summary, as well as the average value for that vector here. All right, what if we want the first 10 elements? Well, a few ways to go about doing this. We could use head, just like we did for the data frame. Head x comma 10 would be the first 10 elements. We can run and see that as the first 10 elements. Or we could alternatively just do x and then refer to those elements directly by putting square brackets and then a vector of the elements that we want. So 1 colon 10 is a shortcut for 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Same way of getting to that answer here. And then finally, finding the sum of all values of x. Well, the command is sum, as you might expect. Sum of x is going to give us the sum. If we run this line, we see that the sum of all the values is 642.9. Okay, so we worked with the vector x a little bit, just some basic commands that we often do. Now let's look at some of the elements themselves. Part B wants us to print to the screen the 2nd, 17th, 26th, and 32nd elements of x, and then also find the sum of those 4. All right, well, how can we refer to specific elements of a vector? Well, we type in the name of the vector and then we put the square brackets. Inside the square brackets, we can put numbers that correspond to the positions that we want to look at. So if I wanted just the second element, x square bracket 2, would do that. That would tell me what the second element of x is. But in this case, I actually want to see 4 elements essentially at once. So I don't have to be restricted by just putting in a number here between the square brackets. I can put a vector of all of those elements that I want. So 2, 17, 26, and 32. We'll go ahead and print out those corresponding elements here. All right, so those are the 4 elements that I requested in the activity. Now, if we want the sum of just those elements, well, we could type out that sum manually, but why bother? We know the sum command exists. And I'm just going to go ahead and copy and paste what the values are that we want to be taking the sum. So this will look and say, okay, you want the sum of something. All right, well, let's look at the vector x and specifically the elements that you requested, and we'll take the sum of those 4 numbers, 84.4. All right, part C is going to have us do a little practice with the which command. So we're asked to find the elements in what positions of x are greater than 20. Is it the first element, the 10th element, the 50th element, etc.? You can see that if I were to just type out x down here and look at all these elements, all right, well, which ones are greater than 20? Well, the first one, the second one, the third one, the fourth one is. But I don't want to waste my time at going through this vector. There's a better way of doing this. How can I figure out which elements meet a certain condition? Well, that's by using the which command. So the which command tells us what positions inside of a vector meet certain conditions. How does this work? Well, we simply say what condition we're interested in checking. In this case, we're interested in knowing what positions of x are greater than 20. So if we ask which x greater than 20, that'll go ahead and print out all of the positions where there are elements that are greater than 20. So the first element, second, third, fourth, and eighth. And we can see that that corresponds to the elements of x if we were just to read it out loud here. So a nice quick way to find the positions inside of a vector that meet a condition. All right, what about the positions of elements that are between 17 and 18? Well, whenever we're asked for positional information, where inside of a vector, what element number, we know we'll use the which command, and we can combine conditions. So between 17 and 18 really means greater than 17, but less than 18. So I can type out both of those conditions here, separated by a special symbol. So I want to make sure that the elements are greater than 17, and I want to make sure that they're less than 18. The and symbol in R is the ampersand symbol, so I can type in which x greater than 17 and x less than 18, and that'll go ahead and that'll print out the positions inside the vector x that meet those two conditions. So I see the 11th and indeed the 13th meet those conditions here. All right, the last part says, well, how many elements are less than the average value of x? And there's a few ways to go about doing this. Let's do this the efficient way. Basically, if we want to know how many elements are less than, say, some condition, we would be able to use the which command, basically figure out what positions inside the vector x meet that condition, and then count how many there are. So the length command tells us how many elements are inside of a certain vector. And so if we put in a which command inside the length command, that'll get the job done. If we ask which x is less than the mean of x, well, this inner part here, which gets parsed first, is going to print out the positions inside the vector x that have values that are smaller than the average value of x. And then the length command applied to that is going to count up how many there are. So let's just see how this works. How does R actually parse this command? Well, R goes in as far as it can inside the parentheses to start evaluating things and then works its way outwards. So the first thing it's going to look at actually is mean of x. That's the thing that's buried deepest inside the parentheses. So if I just highlight that and run that part, it says that, okay, the average is just about 20. All right, well, which elements of x are less than 20? Well, the 5th position, the 6th position, the 7th position, etc. Looks like I have a pretty long vector here. So how many elements are less than the average value of x? Well, let's use length on the output of that vector here. So it looks like there's 18 elements of x that are less than the average value of x here. All right, so moving on to part D, it says that the smallest and largest values of x are 10.4 and 33.9. Now, we saw that when we did the summary of x, and so we're going to work with that information. So, how many elements of x are integers, and what are their values? All right, well, there's a few ways to go about doing this. The most efficient way, according to the hint, is going to be using the percentage in shortcut. But let's do it the inefficient way first, just so you can kind of see how this might work. All right, so we know the smallest and largest values are these two numbers here. So we're basically checking to see, all right, well, is there an 11 in the vector x? Is there a 12, a 13, a 14, etc.? So, all right, how could we do this the long way? Well, we could ask which element of x is equal to, say, 11. It'll go through the vector x, it'll check to see if any of those elements are equal to 11. If so, it'll tell us where that is. And if I run that line, it comes back with integer 0. Basically, there is no position inside x that is equal to 11. All right, well, what about 12? Nope, I don't see a 12. I don't see a 13. This is a waste of time. We don't want to do this the inefficient way. So one way you could do this is to ask a whole bunch of conditions simultaneously. You could ask, all right, well, what positions of x are equal to 13? Or the pipe symbol here, x is equal to 14, or x is equal to 15, or x is equal to 16. You can see this is inefficient as well. But if I were to ask this, it would say, all right, I'm going to look through the vector x, and I'm going to print out the positions where I see a 13, or 14, or 15, or 16. Do we see any inside so far? Well, yeah, actually the 31st position looks like it's one of those four numbers here. We can verify that by saying x square bracket 31. Indeed, that's a 15. But you can see this would be fairly inefficient. I would need to go through and check 11, 12, 13, 14, 15, 16, all the way up to 33, because that would be the largest integer that I might be able to see. All right, so how do we do this the easy way? Well, the percentage in shortcuts. What I'm going to do is I'm going to delete what I've written right here, and I'm going to ask the question, which elements of x appear inside this vector? And this vector is going to be 11 through 33. Notice those are the only integers that are in between this range here. And so what this percentage in shortcut accomplishes is basically a whole string of ORs. Do I see an element of x that's equal to 11, or equal to 12, or 13, or 14, 15, etc.? So what this will do is it'll go through the vector x here, and it'll check the elements, and it looks to see, all right, well, is that element inside this list of values here? If so, it'll report the position back. If not, it'll move on to the next element of x here. So if I run this command here, I find that looks like the 1st, 2nd, 27th, and 31st elements of x happen to be integers. All right, well, let's see what those integers are. That's what were actually requested right after this. And we can do this just by typing out the name of our variable x and then putting in square brackets. We know the positions of x that are allegedly integers, so let's extract those positions of x. Just copy and paste this command and run it. All right, and we see, yeah, we have a 21, we have a 21, we have a 26, and we have a 15 here. So we've effectively extracted or figured out what integers are inside this column. All right, a little bit more practice here with vectors. We're going to create a vector called y, which is the fuel efficiency, but expressed in kilometers per liter instead of miles per gallon here. So we're given a conversion factor, 1 mile per gallon is 0.425 kilometers per liter. And after we define that, we're going to add this to the MT-CARS data frame. We're going to add a column to this data frame here. All right, so let's create a vector called y first. We'll create the vector and call it something with y with the left arrow symbol here. And basically what we wanted to do is we wanted to equal the MPG column of the MT-CARS data frame, but then multiply by 0.425, the conversion factor. So I can extract the miles per gallon fuel efficiency by just referring to the name of the data frame, MT-CARS $MPG. And I'm going to multiply that by 0.425. That's going to convert the miles per gallon into kilometers per liter here. So I'll run this. Notice it appears in the environment. And now to add that to the MT-CARS data frame, I'm going to use one of the few ways we can do that. We're going to type out the name of the data frame, MT-CARS. And if I want to add a new column, all I need to do, put on the $, and then say what the name of that new column is going to be. I say to call it KMPL here for kilometers per liter. And I'll use the left-hand arrow symbol to define that as a set of numbers here. Well, I just figured out what those numbers are. I want that to be the value stored in the vector y. And so I'm going to run this line. I'm going to watch what happens to the MT-CARS data frame up here on the right. So I'm going to run this. Notice it went from 11 variables up to 12 variables here. I can look at the first few rows of MT-CARS, and I do see that indeed kilometers per liter has been appended as a new column in the MT-CARS data frame. All right, so we're happy with that result here. And I'm going to stop the recording before we go on to number 2, because this is getting fairly long. Actually, but before that, I've done some work. Now I'd like to knit it into a document, either in HTML or into a Word document. How do I do that? Well, the knit button right here, I can just click that, and it'll do whatever the default is set up, or I can select this little arrow here and say either knit to HTML. Don't select knit to PDF. It won't do it without the installation of a lot more packages. Or I can knit to Word. I'm going to knit to HTML because it tends to be a little bit easier to start out with. And you'll notice the very first time it tries to knit, it says, hey, guess what? You need a lot more stuff to actually do this knitting. So what you're going to say is, yeah, I want to install these extra packages. And you're going to cross your fingers because this doesn't always successfully install. Pay very close attention as this is running through the installation process to verify that all the packages actually successfully installed. Very often it won't do it and it'll say, hey, package JSTAR wasn't successfully loaded. What do you do in that case? Well, you go back down in here and you just say install packages, whatever the name of the package that was not successfully installed. Keep doing that iteratively, and eventually you'll get to a spot where it knits correctly. So here I'm going to click knit again, and there we go. It's all nicely embedded in here, the commands, and then also the output. And so we're doing good, making good progress with this activity.